Yes, thank you all for being here. As Maria already pointed out, this is a collaboration between the best chapters, Unite. We are the local chapter from the Netherlands, and the student chapter is from the National Polytechnic University in, as you can see down there, and they are the best student chapter of this year. So first, let me quickly see, there we go. Introduce our local chapter in the Netherlands. As you can see on the left here, this is our current board, which is a very talented group of people, and me. I'm the vice president. The president, Florencia, is here as well, along with Dr. Dong Zhang. We organize a whole bunch of events in the Netherlands. Generally speaking, we organize in-person events, as you can see on the bottom right, for example. And we are a relatively new chapter. We were only formed a few years ago. We've also previously won the best new chapter. You can see a picture of our previous president, Diego Rovetta, accepting the prize in the bottom. And yeah, if you are in the area of the Netherlands, we try to organize an event every month. Sometimes they're live, sometimes they're online. And we also organize a yearly barbecue during the summer, and we have some really, really interesting events planned for the next year. So if you're in the area, come say hi to us. And then I would like to give it over to my colleague from the student chapter. Here we go.
So Hasai, if you want to introduce your chapter and yourself, please go ahead.
Thank you so much. Good afternoon and good morning to all the people who see in this moment. Well, this year, the EAGE Student Chapter focused on making itself now open national leave, and since its many events focus on this dimension of the earth science and its behavior to the general public, participating in events such as Tierra Fest and Congress of the Water, RAO-GM, and the most important for us, roundtable in the Senate of the Mexican Republic. We have to work hard to demand our work as well to provide knowledge to our students to excel in the earth science. So we feel very excited to be the best chapter. So, well, I don't know more, but thank you so much for this, and it's all.
Thank you, Hasai. So we can move forward with the next slide. Jerry, please. Good, thank you. This is a very special invitation we have for you all, especially for the ones who are not part of the EAGE as an EAGE member. So become an EAGE member now and benefit from, we have a lot of benefits from the ones who are not part of the EAGE itself. So we have some membership recognitions program, access to support programs too. You can also access to the platform. We have more than 70,000 papers uploaded over this platform. We have also some discounts on events and courses. You can also access to highlight grade geoscience journals. We have actually 5. Free webinars and learning resources from our association that you can access to. And we also have some dedicated technical communities. So if you perhaps are interested to be part of the EAGE and you want more information, please don't hesitate to let me know. And for sure, I will be able just to share more information about this. Next slide, please. Thank you. So today we have 2 amazing speakers. The first one is Professor Feven Desta, assistant professor from TU Delft, the Netherlands. She's going to talk about enable the energy transition, essential resources for success. And we also have today with us Mr. Chris Nind, Vice President Business of Development, Abitibi Geophysics in Canada. He's going to talk about mineral exploration thoughts from a long-time geophysicist. So before we start with these amazing talks, one of the leadings of the student chapter and the local chapter will be reading their bios just for you to let you know who they are. Next slide, please. Then we have a special invitation for you all. We will host our Near South Geoscience event for the 2024. This is gonna happen in Helsinki, Finland from 8 to 12 September. So we already have all the information posted in the website. If you want to be part of this event, you just have to go to the EAGE events website, and for sure you will be able to find out the information there. On the 5th, we will have conference on geophysics for mineral exploration and mining. So please do not hesitate to drop us an email if you want more information about this amazing event. Next slide, please. And from the Americas region, we have the first EAGE Symposium on Geoscience for New Energies in America. This is gonna be held in Mexico City in the 2024. The exact dates are about to confirm, but for sure this is something that we are going to announce within our social media and mailing campaigns. The topics that will include within this event is gonna be geothermal energy, CCS, water management with a focus on water footprint, and the pivotal role of mineral exploration in driving the energy transition. So do not hesitate to be aware or to ask more information about these two amazing events that we will host in the 2024. So now I'm going to give the word to Jody, just for you to introduce our first speaker.
Yes, thank you, Maria. So buckle up, everybody. We're going to be here for a while. I've read novels with a shorter bio than Feven. Well, who's Feven? She's an assistant professor in raw material characterization and spatio-temporal modeling of mine waste systems. She has done a BSc in geology and an MSc in environmental system analysis. She thought that wasn't enough, so then she did a second MSc degree in geoinformation for science and Earth observation. She also seems to have had the time to have 8 years of experience working in different companies in the area of geoscience and environmental studies, which has worked as a geotechnical engineer at GISRS, an environmental specialist, and a geospatial analyst. She has also done a PhD which she completed in 2021 on a dissertation titled Sensing and Data Fusion Opportunities for Raw Material Characterization in Mining. And prior to becoming a professor, she also worked as a postdoc in the section of resource engineering at TU Delft. I hope I didn't forget anything. Feven, thank you so much for being here.
Thank you, Jerry.
Yeah.
Please, Professor, go ahead. The floor is yours.
Okay.
I think that you, there you go.
Okay, thank you for the nice introduction. You didn't forget anything, actually. So let me share my slide. I couldn't see the option. Why was?
At the bottom of your screen?
No, I found the share button, but okay, we cannot display your shared content. Make sure that you have allowed permission. I need permission, please, to share a document.
Could you please try it again?
It's the same. Do I have permission now?
Yes, I already gave you the co-host and the presenter role.
Okay. Let
This
me
is weird.
see.
Oh, you're sharing your screen. Yeah, because we can see.
Do you see my slide now?
Yes, no, your slide, but you are seeing your files.
Oh, okay. Let me try again. Sure. Strange, I couldn't see. It worked before, but like, I don't know what's
Yeah.
happening right now. Okay, let me try again. Yeah, I don't see the option. And
Okay, let me check. Can you hear us, Professor Feven?
I can hear you, yeah.
Okay, because you already have the co-host and the presenter role, so
This is the only screen option I see.
could you please? Yes, we are seeing your screen right now. Now you're
Yeah, but like when I get the option, the only option which I see on my screen is this one, like the screen which you see.
yes. Okay. Can we try something very quickly? Could you please try to disconnect and connect again to the session?
Yeah, okay. Let me try that.
Thank you. Apologies for the participants.
As you can see here, the global mining projects are, global mining is, there's project locations all over the world. And in my career, I've been able to work in many of these, many countries around the world. There's still a lot of exploration being done in Canada and the USA, and probably it's the center for percentage-wise the most exploration that's done. But some of the other areas of the world offer tremendous potential for mineral resources, and not too much exploration has been done there. For instance, the Middle East, the Arabian Shield there has some of the best potential in the world, and they're at the time they did this study in 2018, there was virtually no exploration being done for minerals in the Middle East. Today there's a lot of interest in finding minerals in Saudi Arabia, in Oman, and so on. So there's still plenty of areas of the world that are underexplored for mining. Despite the interest in mineral exploration and things, the actual exploration number of discoveries has been dropping, and you can see in a peak of into just after 2005, about 2010, there's a significant number of discoveries, and the exploration expenditures in the red. You can see that with high exploration expenditures, and then, but since then, the number of discoveries has been dropping. The exploration expenditure has been dropping, and it has recently started to level out. Still fairly significant, but for historical purposes, but our discovery rates are not good right now. So how do we get, and the average cost of discovery has been going up steadily, and between 1975, when I started in 2005, the average cost of a discovery was $65 million, and now it's more than tripled that. It's over $200 million, the average discovery cost. So it's the costs have increased and the discovery rates have decreased. That's not a good, not good. Why? One of the reasons, major reasons why, is that we're progressively having to move deeper and deeper into the ground to make significant discoveries. undercover. Sometimes the cover is very conductive, and it's difficult when something just happened on my screen. Can you still see my screen?
No, we cannot.
You cannot see my screen.
Yeah.
Okay. All right. Hang on. Just went wrong. Okay. Try this. Is it back?
Yes.
Okay. I don't know what happened there. Okay, it's going progressively deeper undercover. So the targets are getting more difficult to find. That doesn't mean they don't exist. There is plenty to discover at depth. So we need to know how to find those deposits. And in fact, if you look at the from between 2012 to present, there's roughly 2 tier 1 deposits that have been found every year since 2012. By tier 1, we mean a deposit that is a company making mine. They're more than 20 years mining to mine them out, and they're huge deposits. So you can see in Canada, northern Canada, the Arrow deposit, that's uranium, was found in 2014. There's copper deposits that have been found in Chile. There's zinc deposits that have been found in Central Asia. So it's there are still deposits being found at this rate about 2 major ones per year, world class. The exploration expenditures by commodity is still very much dominated by gold, and about almost half of the exploration expenditures in the world is done for gold, and about 30% for base metals in copper and nickel. This chart was made in 2022, and it doesn't include lithium or any of the critical metals, which we're now hearing a lot about. So I think the updated charts in the upcoming years will include exploration expenditures for the lithium and other critical metals. The critical minerals that we talk about here are building blocks for the green and digital economy. Geoscience and exploration is right at the start of the upstream of the critical mineral strategy. Without geoscience and exploration, we will not be able to make achieve our downstream goals of electric cars and generate our clean economy. We simply won't get there. So we need the geoscience and the exploration on the upstream side. You hear a lot about lithium, but lithium is in fact only one of the critical metals that is in risk for future supply. And on this periodic table shows you in this orangey yellow color all of the elements that are limited availability today and future risk to supply. And of importance, lithium actually, we may be able to substitute lithium with something like sodium, but if you come to copper and nickel, there is no substitute to these. The electric cars have many times more copper in them than a gas-driven car. The batteries in these cars have about 10 parts nickel to every part to everything else. It's your 10, 1, 1 battery, the 10 is nickel. So these commodities are limited availability, so we must find new and develop new mines to deliver these metals to the market. The geophysical solutions for geological environments are listed here. Somehow the table got a little bit skewed here, but if you look at the targets on the left-hand column here, you have diamonds and gold and VMS deposits and so on. The different geophysical methods are maybe some of them are good and some of them are not so good for depending on the geology and the target. So for a commodity like for a VMS target, you could magnetics and gravity and time domain EM and IP are all good, but you wouldn't use a ground penetrating radar as necessary for a VMS target. But success is going to require the integration of geology, geophysics, and geochemistry. There's very few deposits that are going to be found, in my opinion, using only one of these methods. So you need to make use of the entire mineral exploration toolkit to improve our discovery rates. In Europe, starting in 2017, there was a very good incentive. It's called the Smart Exploration Project that, in fact, completed in 2021, but it was very successful and has now been extended. So the Smart Exploration Research Center has been granted a 6-year program commencing in January 2024. And you can see all the partners here. This is for very much for Europe, and it's been a tremendous success. And I would encourage you to get on the website for Smart Exploration, take a look at what they've published, and they have made a significant contribution in way of new instruments, new targets, particular for seismic use of seismic technologies in mineral exploration. AI, artificial intelligence, machine learning have really come strongly on the scene in the last few years. And they are an exciting new tool, but I would caution you to beware of overuse of these tools. There's a human tendency to see patterns and meaning in random information. It's called apophenia, and it was a term coined by a German neurologist in 1958 who was studying the unmotivated seeing of connections in patients with schizophrenia. And this was a recent discussion just this month about this tendency. Kim Franklin, who's a geophysicist in Australia, sent a notice saying our inability to see the pattern could just be excused as human frailty against the omnipotence of the machine. So an apophenia is well exploited by scammers, people who come up with new things that just are scams. So how do we guard against this? And it's important. I believe Greg Hodges just earlier this month wrote, if a case history does not show convincing data where the reader can see the geology and show independent verification of geological interpretation, and if it doesn't make clear how the geology is sensed, then it's just a pretty picture. It's basically not any more than a pretty picture. And Anthony Price, who's another geophysicist, sent this little cartoon. And this is your machine learning system, and the answer is yep. You pour the data into this big pile of linear algebra, then collect the answers on the other side. So the question is, what if the answers are wrong? And the guy says, just stir the pile until they start looking right. The best protection against scammers, and this is just based to rely on basic physics. Now, unless you're an academic, you will not be asked to solve Maxwell's equations or work with these things, but I encourage you to get a familiarity, just a gut feeling, and develop a healthy skepticism. And if you're presented with something that just doesn't seem right to you, ask questions, and seek advice, ask opinions. Most of our geophysics is really based on these Newton's laws of motion and gravity and Maxwell's equations. Scammers if you ask them questions, they'll tell you things like, we can't tell you because it's secret. So beware of secrecy. Beware that their signal often violates the laws of physics. And in particular, their signals don't attenuate. Attenuation is something that often with scammers, they're using a very low power transmitter or sensor, and they're detecting signals from deep underground. It just is not possible. Their signals do attenuate. They love to quote, use the word quantum because nobody really understands quantum physics. Even the people who are in quantum physics don't really understand quantum physics. And so they'll tell you their sensor detects quantum signals from deep underground. Well, this just doesn't happen. We do have sensors that rely on use quantum, like a cesium magnetometer that we use quantum effects, and we have Josephson junctions, and we are with our squid mags, and so they have quantum effects, but that's at the sensor level. From the signal level, we can detect muons that have penetrated the Earth, where at a certain distance. Those are gamma rays that are coming from outer space. They interact with our atmosphere and they develop muons that intersect the Earth. We can see that. And in radiometrics, we do see decay, radioactive decay, but that's only from the top, maybe 50 centimeters of the surface. If you get deeper than that, you won't get any radiometric or signal. The scammers love to also come up with new physics and unexplainable phenomena. And they will quote you, they will direct you to a bunch of technical papers, often written by themselves and published without peer reviews. So just beware of those. The other thing that I see, and I want to stress, machines will not replace geoscientists. I don't believe they will ever replace geoscientists. Because our brain is not a CPU. If you take a CPU and you feed in data, you process it, it spits out a solution. And if you repeat that process, you get the same solution. As long as you don't change the software and algorithms, if you transfer to a different CPU, you still get the same solution. But our brains are more similar to symphony orchestras, and minus the conductor. If you feed in data to our brains, and we process it, and we get an answer, we spit out a solution. If you repeat it, think about it again, do it, think about it all through again, you come out with a revised solution. You take it to a different team, you get a different solution. That's not the same thing as a CPU. So a caution on linear algebra and calculus. They're essential tools. My degree is in math, but these linear algebra and calculus are not final solutions, because geology is fundamentally discontinuous, and linear algebra and calculus work very well on, but until you hit a discontinuity. Geology is fundamentally discontinuous. And the way I think of things as ore bodies or geology's black swans. How do you find them? Well, if you use linear algebra and calculus, you tend to present things as in normal distribution, Gaussian normal distribution. But normal distribution is a extreme case of a class of distributions called Levi stable distributions. And the best way I can illustrate it, if you have a firing squad and you introduce some drunks into your firing squad, all of a sudden the pattern of bullets on the wall will no longer be a normal distribution, because the drunks are just not, they're not the same. They shoot, and some of them may actually shoot parallel to the wall. So this class of distributions called Levi stable distributions, all of a sudden something that is a black swan with a normal distribution, if it's a 5 sigma event, that would be a black swan. The chances of seeing that is getting that is 1 in 3.5 million. But if you, at the other end of the extreme of these distributions is Cauchy distribution, and then your chance of a 5 sigma event is 1 in 16. If you look at this little chart, I've got that the dashed line, the small dashes is the normal distribution, the solid curve is the Cauchy distribution, and the difference is on these tails. The normal distribution goes almost to 0, whereas the in between these distributions don't go quite to 0. And it means, in my opinion, that the chance of finding a large ore body is much better than a 1 in 3.5 million. You have a much better chance. So so geoscience is challenging. It's rewarding. It's a great time. You have a lot of time, people, and opportunity to see the world. Our great unknown is under our feet. We know less about what's 100 meters below us than we know about what's 10,000 kilometers above us. We need critical metals, and one of the paths is we need to change the public perception of mining as dirty. You can't extract ore from the ground without doing some environmental damage, but it's much less than any environmental damage caused by global warming. We need new mines, and we need to develop them with proper environmental controls. So be cautious and don't rush. When you rush, you make mistakes. When I hear people say, or politicians in Canada have said that they're going to take a mine, develop a mine within 2 to 3 years, I get worried that they're going to make mistakes, and mistakes cause environmental problems. Rocks are patient. They've been there for billions of years, and they will be there. So I think we need to be cautious. We need young people with new ideas, and it is a great time to be graduating geoscientists. in geoscience. Don Walsh is an oceanographer who died this month, just on November 13th. And exploration is curiosity put into action. Your students are about to embark on a career that your path is long and exciting. There'll be some storms. There'll certainly be storms along the way, but your future is very, very bright. And personally, my career has been absolutely, it's never been boring. It's always been a lot of fun and very interesting. And thank you.
Thank you so much, Chris. If the participants have any questions, you can ask to the instructor directly as soon as we finish with the second talk. So we are going to have an open panel discussion after this. So if Professor Feven is ready, so I'm going to give you the presenter role.
Yes, I'm ready. I hope this time you see my screen.
Yes, we can. Okay, you can put it on presentation mode. Okay, there you go. Thank you so
Okay.
much. Please go ahead. Thank you.
Great. Okay. Sorry for the inconvenience. Good day, everyone. I'm thrilled to have you join today's presentation on enabling the energy transition. We will explore some of the key resources driving the success of the energy transition. So the energy transition is a crucial enabler of sustainable development and climate resilience. But the question is, how do we enable the energy transition? What resources do we actually need for that? Of course, from Chris' presentation, we have seen interesting topics, which I will also mention some of those points in my presentation. But it's a key question to start with: what resources do we actually need to enable the energy transition? So attributed to population and economic growth and for the need for the green energy transition, there is an increasing need for the mine products. And this leads mining to the extraction of resources from geologically complex regions. These regions are exemplified by low ore grade or deposit at deeper depths. So mining in this area has its own challenge and could result also with the production of a huge amount of waste material. So this has implication on the energy cost, and it also has implication on the environmental footprints. But the question is, how can we meet the demand for mine products while simultaneously reducing the environmental impact of mining? So one justification for asserting a growing demand for mine product lies in the fact that the energy transition is mineral intensive. To put this into context, let's take two examples. One, a wind turbine. Just to build a single wind turbine, we need a huge amount of metals, for example. We need about 4.7 tons of copper. That's not the only metal which we require for that. We need aluminum, rare earth elements, zinc, all other different kinds of metals. Again, let's take another example, the minerals for electric vehicle and versus the gas car. The one which you see here on the in the black circle shows the mineral required for the gas car, and the one which you see here in the green circle shows the mineral required for the electric vehicles. As you can see, let's look up for copper, for example. We need about 22.3 kilograms of copper for conventional gas car, whereas we need about 53.2 kg of copper for electric vehicles. So in general, an electric vehicle can have 6 times more mineral than the conventional gas car. So the deployment of this clean energy technology requires a huge amount of mineral. Now, it raises a question: how are we going to supply these resources? Is it from primary source, or is there other alternative from secondary recovery, for example, or maybe recycling? we will look at it. Okay, so this was also a societal challenge because the need for a huge amount of metal would have implication on the waste production. For example, let's take one commodity, copper, as an example. And if we mine copper at the cutoff grade of 0.5, it means that we will produce about 99%, 5% goes to the waste material. And it's a huge amount of material will be dumped as a waste. Let's look at it also from other perspective. This is an interesting infographic to visualize the size of the world mine tailings. Tailing is, they are the leftover from mineral processing, and they are water-based slurry actually, and they can be stored on, in ponds or dams. So according to the Global Tailing Review estimates, there are about 8,500 tailings. This could be active, inactive, and closed storage facilities. And when they estimate the amount of tailing, it's accounted for 217 cubic kilometer. So to compare it with, for example, what you see here is Manhattan, and like the global tailing has this volume and with a 6 kilometer height. What makes it even very interesting is there is an annual growth of about 12.3 cubic kilometer. So even though the amount of tailing production varies from commodity to commodity, there are, of course, different factors that could determine the amount of tailing, the quality, quantity, the type of material. But with the increasing need for mine product, even this production will, the waste production will grow up. So now tailing is one waste stream, but there are different hotspot regions along the mining value chain which could possibly generate a huge amount of waste. For example, if we look at mine life cycle here, there will be waste rock production. That's a material that will be removed to gain access for ore. And when this ore is processed, tailing will be produced, and also after geometallurgical processes, slag material could be produced. But if we think of like the remining concept, because recent study shows that there is a possibility in finding different critical raw materials in the waste material with different concentration, of course. Is there a possibility to recover these elements of economic interest from this waste material? Then if that is the case, then there is opportunity for remining along the mining value chain at different waste stream sites. And it triggered the question, is mine waste an alternative future resource? That could also be like very interesting question to look at, but it has some other implication where the economic model has to be developed and innovative mineral processing approach should be developed as well. So promoting this efficient utilization of natural resource and minimizing the environmental impact through elimination, reprocessing, reusing, and remining could help us create a responsible mining. And also this concept fits in the circular economy concept. Now, there are different innovative mining approaches that could help us realize responsible resource extraction. But when we think of solution, we need to come up with a solution along the mining value chain. So there is an innovative, there is a need for innovative technologies in mineral discovery of new resources, and extractive methodology, and we need also innovative technologies in mineral processing and waste management. Just to show you some of the examples which could get like emphasis, it's not limited to this innovative mining approach. There could be more approaches that could help us achieve responsible resource extraction. But here I would like to focus on three main things. One is remining. That's the secondary recovery from waste material. And the other one is smart connected mining. That's the digital transformation of the mining system or the whole mining system. And proactive mine waste management and monitoring, which could help us reduce the environmental footprint from mining. So for this, we need to understand the concept of this temporal evolution of materials at waste dump sites. For example, we need a model that could predict mineralogical composition change because it has implication on the secondary recovery and also implication on proactive mine waste management. So we need to measure them, we need to model them, monitor, and then predict. But what are the tools that could enable us to measure the composition or material? Sensor technologies are one of the tools which could help us achieve a compressive material characterization. And there are various sensor technologies that operate over the wider range of the electromagnetic spectrum and provide information on different material properties. And this technology could operate from different platforms, from spaceborne. There are spaceborne technologies, airborne technologies, ground-based technologies, and also geophysical techniques to understand the subsurface. This technology provide multi-scale data, and they could provide image data, point data at different scales. So the utilization of this data could help us generate the key information or knowledge on the key geological attributes in mining. These are the mineralogy, geochemistry, fragmentation, or textural information. So just to show you some of the examples of possible portable sensor technology, as you can see from this image, we have infrared technologies that could provide mineralogical information, and portable XRF, that's a geochemical technique, and Raman technology, which could also provide mineralogical information. But there are sets of sensor solutions from different suppliers. So what is the value of the utilization of sensor technologies in mining? They do have different benefits. For example, it will improve grade control. It could also improve process control, improve safety. It will enable us to achieve automation or real-time material characterization, for example. And also these technologies could be mounted on the site so that we can produce in situ characterization that could help us to make a rapid decision or a quick decision to enable effective decision-making in mining process. So just to show you some sensor measurement opportunities in the underground and open pit mining scenario, as you can see from this schematic sketch, there are different potential sensor installation sites that could help us characterize material at different spots, and also could also help us in material tracking. For example, one possible application is mine face mapping for open pit mine, or drill core scanning, or technologies can also be used over the conveyor belt to sort material, for example, waste material streams. Same is true for underground mines. As you can see here from this schematic sketch, it's possible to utilize technologies in the underground mine. But for most of the technology, it's not easy to take the technology in the underground because most of the techniques are not robust to tolerate the harsh environmental condition in the underground mine. However, there are robust technologies which are under development and already developed techniques which could be utilized in underground to generate, for example, a mine face map. And I have one particular example to show you on the next slide. Slide after this one. So sensor technologies could provide data, but it's complex data. It's very complex data which we cannot understand by visual inspection, or we cannot understand by intuition. So we need a data-driven approach to generate information or knowledge out of this This data-driven approach could be data mining, machine learning techniques, or signal processing techniques, which help us to enhance the signal of the mineral or the elements and minimize the noise in the spectral data. Just to show you how material can be characterized at different levels, I would like to use this schematic diagram. So you have basically the sensor data, and then you can apply different machine learning technique or data fusion. That's like integration of different sensor model to enhance information. That's also possible. So you generate information which are the key attribute, let's say, in the mining. This information can be generated at different levels. For example, you can use it to detect or determine the presence of material. That's called detection. Or you can classify material into ore and waste. That's called discrimination or classification. And also technologies can be used also to fingerprint individual entity under investigation. That's identification of, it could be minerals or elements. And also it's possible to utilize technology to quantify the presence of certain material. So depending on the intention of the project or depending on the usability of the technique to achieve such levels, it's possible to investigate all the all these options. Now, this slide shows some application examples from our section outputs. The one which you see here on the RGB imaging, this image were acquired in the underground mine using RGB camera. So what we have tried to do is to map the minerals mine face. RGB imaging, it's a 3-band information, so the information is limited. However, it can be applicable to map minerals if the minerals are visually distinct. So we need to see, and this is a polymetallic sulfide deposit where you can differentiate, for example, the galena from chalcopyrite. But it also has some limitation, for example, in distinguishing between pyrite and chalcopyrite because the color is somehow closer. The other technology is hyperspectral imaging, and we utilize this technology to generate map using the drill core data samples. And we used a hyperspectral image that range from visible to shortwave infrared. So the visible infrared region enable us to identify some of the iron oxide and also some of the sulfide mineral using the pattern. They don't have characteristic absorption feature, but the reflection pattern could be related with sulfide minerals. And the shortwave infrared region that enabled us to identify alteration mineral in the drill core. The other technique is mid-wave infrared and long-wave infrared. So we test this technology to see the possibility of classification of the combined lead zinc ore from waste material. Raman is utilized to identify, that's a laser-based technology, and it was used to identify some of the minerals in the analyzed sample. LIPS is the other technology, is laser-induced background spectroscopy, laser-based technique, which could be utilized to generate information on the elements. And it's very good to detect lighter elements as well. And we utilize it in another application to understand the composition of lithium ore samples. So basically what we have done is try to assess the possibility of utilizing the technique to characterize the material at different levels. The first step we did was identification. So can we detect the lithium peaks in the sample? As you can see here from this spectral plot, yes, it was possible to lithium. Then the second one is the classification. Can we classify the lithium ore and waste material using different cutoff grade? Here we have tried to optimize it for the threshold value where the technique could efficiently provide or very good classification accuracy. So we didn't directly apply the market cutoff grade, but we just test different cutoff grade. And the interesting fact is the technique works better to classify with a lower cutoff grade, and it shows the possibility of application of the technique for characterization of material in low-grade deposits. The other approach we used is to test the possibility in the prediction of lithium. The achieved result is not as we expected. It was not easy to develop the calibration model for this. However, compared to the lab technique, of course, it depends. However, for rapid determination of material, still we believe that it could provide some usable data. So to conclude my presentation, energy transition is mineral intensive, but we need to somehow come up with a proper approach where we balance the demand for the mine product while simultaneously reducing the environmental impact of mining. So we need to consider responsible mining where we maximize the use of resource and minimize the environmental impact. For that, we need innovative solution in extractive technology, processing technology, characterization technologies, not limited to this, but we can maximize our approach by considering innovative technologies and innovative data analytics approach, advanced data analytics approach to generate knowledge out of the different sensor technologies. With this, I conclude my presentation. Thank you for your attention.
Thank you so much. Now I think that we are going to give the space for the open panel discussion. So if any of the participants have any question, please turn on your microphone and ask directly to the instructor. Please go ahead. I think that we have Adnan.
Yes, I
Please
just
go
want
ahead.
to ask. Can I ask the question?
Yes, please.
Okay, so I want to ask a question related with what is the role of sedimentary rocks in the exploration of critical metals during energy transition? So sedimentary rocks have some potential of critical metals like lithium, nickel, cobalt, or we will go towards hard rock, mean igneous rocks or metamorphic rocks for lithium, nickel, and cobalt or other critical metals during the energy transition.
Okay, let me, this is Chris. Let me answer a little bit about it, and then I'm going to defer to Feven. There is a type of deposit called SEDEX, which is some of the examples SEDEX deposits around the world. And so you can find if you go on the website, SEDEX deposits are basically minerals and metals that have spread out in through sedimentary rocks, and sometimes you'll find that if you drill through sediments, you can see some cases of SEDEX developments. So there is applicant, but I think most of your VMS deposits and things are in your rocks, so not in your sediments. I defer this to Feven. Can you want to answer about the lithium?
Okay, so like for the lithium, yes, we, for example, for our study, what we found lithium, you can find it in the barren deposits, and you can also find it in the pegmatite deposit. So for the one with the example which I showed you, it is in the pegmatite deposit, which is igneous one. And within that, there is like different minerals like petalite, for example, spodumene, which could source the lithium in the pegmatite.
Thank you so much. Is there any other question from the audience?
I'll ask a question of Feven, if that's okay.
Yes, please, Chris, go ahead.
I'd like your, it seems to me when you, when in the tailings of mines, you have taken the rock and you've ground it up and you've increased the surface area dramatically. So you potentially have, I guess I'd think of it as alteration on steroids. Have you, what do you think of the possibility of using tailings for carbon mineralization?
Tailings, depending on from which primary source they come, they could vary compositionally very high. That also depends on the processing chemical they add during the process. But as you said, there could the increasing of the surface and the exposure for water, and also the exposure for the water could facilitate changes or chemical changes in the composition. So it could contain some hazardous material that, like, when it could be applied for re-extraction, it should be investigated compositionally, and then that could also completely vary depending on the deposit type. For example, for one of the gold deposits in South Africa, there is also a possibility to get the uranium in the tailing material. So what we are investigating has to be first assured with a comprehensive compositional analysis to propose it whether for secondary recovery of certain material or for using it, for example, for different construction material or other kind of application. So my quick answer would be compositionally, it could be highly variable. First, depending on the ore type. Second, the change, because there's a dynamics which going on because it's exposed to water, it's exposed to different chemicals added during the processing. Compositionally, we need to understand what it consists before we suggest for its application for certain different types, I would say, for certain things.
Good, thank you.
Thank you so much. Any other question, perhaps? It seems that we don't have more questions, so I think that we can close the session right now. Thank you so much, Chris. Thank you so much, Professor Feven. Thank you to the EAGE student chapters and, of course, the student chapter itself and the local chapter. Thank you so much for being here today and for hosting this amazing webinar. So, Jody, if you want to perhaps say something, please let me know.
Well, I would like to also thank the speakers on behalf of the local chapter. I thought it was both two very interesting talks. So thank you so much for your time and definitely giving me a lot to think about. And thank you to the EAGE and the student chapter as well for everything they've done for this event.
Yeah, thank you. Thanks to you.
Yeah, thank you for the invitation as well.
Yes, thank you. Oh,
Thank
and your question about the presentations, I have no problem sharing the presentation. I can send it to you.
Okay, got it. So please just.
Yeah, I can.
Okay, good.
I can also share my presentation. No problem.
For sure.
Yeah.
Then I will be share this presentation with the participants. So no worries about that.
Thank
Thank you so much. I think that this is it for today. Hope to see you soon in our future events for sure. Thank you and have a nice weekend ahead. Thank you. Bye-bye.
Yeah, thank you. Have a nice weekend. Bye.
Thank you.
Bye-bye.
Bye-bye.
Enjoy yourself,
Bye-bye.
everybody.
Thanks for everything.
Bye.